here the shape of the drum. We're going to take of a band, sorry. Can you hear the shape of many, many drums and band, at least 2 drums? Can you hear the shape of the band? And we're going to take Ori out for dinner in the usual place. If you'd like to join us, please let me know immediately after the talk. And sorry for being 1 minute late, so you have 48 minutes from now. Thank you.
Thank you for the invitation. I'm happy to be here again. I'll talk about can you hear the shape of a band. But before that, some history. The original question is, can you hear the shape of the drum? And that was asked by Mark Kac in a paper which appeared in '66. It's not clear whether people asked this question before, but he gave it this nice formalization or title, and that title, I think, gave this question a lot of attention. So the question is, can you listen to a drum? And now by a drum we mean a shape. Construct a a frame, put some membrane on it, and you hit it, it will make some noise. Can you reconstruct the frame from the noise that it makes?
Does it have to be polygonal or?
So it can be polyhedral. The question is still interesting for smooth drums. You could ask for drums in high dimension, maybe without a boundary. And yeah, you can now separate it to a lot of questions, and people are working on all of these questions since 1966. So what is the sound that a drum makes? So there is some differential equation called Helmholtz. Helmholtz equation. I learned that very recently. And it said that if the Laplacian of the shape times some function is lambda times the fraction, so if I have f, which is an eigenfunction of the Laplacian, then it means that the drum makes the lambda square. It's a frequency.
Within this condition, boundary condition, is the only.
Yes, I'm not going to enter these details. Right. So in this PDE, there are boundary conditions. For example, if there is this frame, and the frame keeps the boundary still. So just for one example, here is a string. And let's say that the length of the string is pi, and then in this case, the Laplacian is the second derivative of a function. And then you know what f are eigenfunctions of the second derivative. It's things of the form sine.
Yeah, but that's what you all means. You have to nail it down at the boundary. That's the boundary condition.
So yeah, so this is really a string. So the boundary is fixed and everything.
Yeah, that's what you all meant.
Right. So okay. So in addition, let's say f0 and fi is 0, and then everything that can happen is this. So I have 1 frequency, 2 frequencies, 3 frequency, etc. And they correspond to these n, and each n will give me the sound n squared. So the spectrum, the set of sound which will be heard eventually is all the squares. It doesn't go up?
It goes up.
It goes up.
Yes.
I have to eat breakfast. Okay. So we don't really care about the analysis in the picture. We're not going to do any analysis, and I really don't know how to do analysis. Some history. So already in '64, Milner constructed, or let's say pointed out, you can construct different but isospectral. Isospectral means that they have the same spectrum of the Laplacian, which means that they sound the same. 16-dimensional drums. Drums. Actually, they are toroid, so they're manifold without a boundary. And I say pointed out because this is a paper which is half of a page, and it just points out that some cool stuff from the 20s in number theory can actually use to do that. You just observe that. And it appears even before Kac's paper appeared, but I think it was an answer to this question. And then began the race from 16 dimensions to dimension 2, where drums actually live. And then through the 70s and 80s, people constructed things in lower dimension. I'll mention two. I'll mention Conway and Sloan because they are local celebrities. So they did 4-dimensionals. Somewhere in the 80s, I'd say 80s, I don't remember exactly the date. And eventually, then there was an important breakthrough due to Sunada in '95, which gave some general recipe. Some general recipe for constructing things like that. Not an actual construction, he did give example, but he gave some general recipe, which I will explain today. And eventually in '92, Gordon, Webb, and Wolpert answered the original question. And the answer is no. So,
yeah. Can you switch off the light over there?
yeah, that's what I'm looking for. Oh, so here's the answer. Due to, this is Caroline Gordon, David Webb, and Scott Wolpert. I forgot his team. These are two drums. These are the membranes. This is the frame. And they sound the same. And then, so this was their construction. Then some physicists went and actually tried to verify this by numerically computing these eigenforms and the corresponding eigenvalues. And you can see that the 50th eigenvalue of these drums coincide up to, but they really should coincide because that they have a theorem, right? They did give a proof. Right? Physicists want to see that things really happen, but it's also interesting because there is no formula like we have for the spectrum of a string. This n squared, this nice n squared formula. We don't have any formula for the spectrum of this thing. It's a complicated PDE. You can start computing stuff numerically, but I don't think there's any hope of finding a closed expression for the spectrum of these.
Did people actually make extra drums and try to do it musically?
So I don't know if the people who did this only did like MATLAB computation, but definitely some people bought these, built these drums and recorded them, and it was very cool. And here are, these are Caroline Gordon and David Webb, two of the constructors. So this is some earlier prototype. It's a bit less nice, but you can see on their shirts that they have prints of these drums. Okay.
So that came later, right?
What?
The original one was more complicated. So here's an example.
Yeah, this is the first one, but then they had the nicer ones. Oh, and there was a question here about polyhedra. I think even today the question for smooth drums is open. I don't think anybody knows whether you can hear the shape of a smooth drum.
No, Mark Kac proved for really smooth, I think it's true.
No, he proves some.
For some
very-
conditions. There are some.
So what Mark
Or
Kac-
convex.
what he did in his paper is show that you can hear some, he called it hear some basic invariant, like the area of the drum or the perimeter, but not the entire shape.
But for really, really nice family of shapes?
Oh, maybe like a family of ellipses. Some,
Yeah.
yeah. For some families, yes. And people did more families like this later. Okay. So this is the history, and what I want to show you today is how to do these things, how to construct isospectral drums. And the question becomes nicer and easier, but more fun when you think not only about drums, but also about ensembles of drums. So now I'm talking about two drums and other two drums, and these together sound like these two. And it all boils down to this. This is what I'm trying to convince you. So this is the nice formula that you use a lot. Actually, today I taught Diffie-Hellman key sharing protocol, which also uses this nice insight. So Diffie-Hellman used this in model arithmetic. Everyone here used this in real numbers, and I'm talking about a different context. So when you prove this in school, you do this by some induction or I don't know what, but then you come to university and you learn that there are sets, don't cover your ears, of infinite size. And there are different kinds of infinity, not attack me. And
Say so-called infinities, then
so-called infinity, and you want to prove this for general cardinals. And then your argument, I think, had to be like this. By definition, if these are cardinal, then a to the b is the cardinality of, so you pick a set A with size A, a set B with size B, and a set C with size C. And your argument is that this is the size of a set of function from B to A, and these are the function from C to the set B to A. So these are functions from C to the function from B to A, and this size is the function from the Cartesian product of B and C to A. And we're trying to show that these have the same size. And the argument is just that you have a very clear correspondence between these two. What happens here? These are functions from C, so it's function, they get something in C, and then they return functions that want something in B. If you give them something in B, they'll spit out something in A. These guys are also functions, but they ask you in advance to give something in B and something in C, and they spit out something in A. So there's no difference, right? So you need to plug in something from B and something from C, and get something from A, and here as well. So this is what we should have in mind. I'll write this in another way. Let's say the functions from A to functions from B to C correspond to functions from A times B to C. And then we try to mimic that in other situations. So in algebra, we have vector spaces, and we look at linear maps. And let's say we look at linear maps from a vector space V to the linear maps from W to U. And we try to simplify this. So say this was V to the WU. And I would want to make this something simpler. And so I don't know who thought it, but probably some of you know that this. Let's say first try what we would first try, which is take V times U. Sorry, V times W to U. That could be a good first guess, but it doesn't really work because here I have linear function which get a vector in V and vector in W and spits out a vector in U. Here also, these are linear functions, they get a vector in V, then a vector in W, and spit out something in U. But here, the linearity means that if I take alpha V, alpha W, the alpha goes out. And here I have twice linearity, and when you check the details, this linearity tells you that any alpha you put here already goes out, and this linearity tells you that if I put beta here, they both go out, and I'm getting alpha V T V W. So it's not the same thing. This function has more structure than the function here. So what we do instead of VW, we define the tensor product, which is V tensor W. And this is more or less take the Cartesian product, but then also divide by relations. And I want the relation alpha V W is equal to V alpha W. After I take the relation, how do you call it, congruency classes of this equivalence classes of this equivalence relation, I'll get this type of linearity, because now I have T, let's say alpha V and beta V W. Now we don't write the comma, we write this with the tensor product to indicate this lives in the tensor product. And now we can move this alpha and beta around. So by definition, this is the same as alpha beta V times W, and also V tensor alpha beta W, and it also goes up. So now this tensor product encodes these maps. And really this is the motivation of tensor product. So if you ever learn tensor product, like physicists do without any explanation, this is, I think, the explanation. That is the meaning of this object, something which encodes this tower of exponent. So I claim that most of these isospectral examples come from this, from tensor product. And it goes like this. So I'm not thinking about sets, and I'm not thinking about vector spaces. The objects I'm thinking about are G-sets. So who ever heard about this algebraic structure? Good. So G-sets are sets. So a G-set X is a set equipped with an action of G. And G is equal to fixed. So this will be like a S4 set. A set with an action of S4. And action means that I can multiply an element of the group by an element from the set, and I get back something in the set. So this is back in X. And there are two things that need to be satisfied. G prime X need to be G prime X. You need to have associativity, and the identity element should have trivial. These are the only assumptions. And the last thing we need is what are the functions. So here we had functions of set, here we had linear functions. When we're talking about G-sets, we're talking about function between the sets that respect the action of the group. So we'll write a function which respects G from X to Y. So if X and Y are sets with an action of G, then these are all the functions from X to Y which respect the action of the group. So it really looks like the part of linearity with the scalars. The scalars go up. So this is really the same, but the scalars come from a group, not from a field. And what I want to understand are functions from a G set to the functions. So these are functions which respect an action from G set to functions from another G set to any set. So this is any set, and this is again a G set. You want to show G? No, No, because this is a set, so this doesn't have an action. These are just all functions, and G also acts on the function. So why? This is very important for us. So let's bring back geometry into the picture. So let's take G to be the group of size 2, and G acts on the square. So let's call the square S. And I'm interested in functions on the square. So I look at functions from the square to the reals. These will be my waves. These will be like for every point of the square, when the square is rotating like a drum, there's the altitude of this point. And this thing is function from the square to the reals. And because G acts on the square, G also acts on these functions. So, I didn't say how G acts, and what I meant is that, let's say this is by reflecting along the middle. So there is one non-trivial element, let's say it reflects. And then, what is this action? If I have some function here, I know what it does. I reflect. What tau will do is to reflect it. This will be important for us later. So this is what you should have in mind, that it goes in generality. If I have a set here, not necessarily R, because G acts on Y, it also acts on functions from Y. And I'm looking...
It's like in combinatoric Fourier theory. It's a bit similar to Fourier theory.
To what?
To Fourier theory.
Oh.
In combinatorics. They have a group action.
Oh. You'll have to teach me.
Okay.
I know Burnside theorem. I think this is the beginning, right?
Yeah.
But I'm looking for an object which will encode this, and the idea is, we already said that this kind of look like what we have in vector spaces, the linear functions, and it really is similar to the tensor product. So this really looks like G function from what I'm going to call the tensor product. S and Y, denoted like this, to S. Sorry, not G. There's no G. And this X tensor product with Y is really, for the same reason that we saw here, is the Cartesian product, but then I need to impose some relations, and the relations are that gxy should be equal to xgy for all g in g, x in x, y in y. And this is tautology. I mean, like you did in the set, you said, this is something which is this and is this and splits this. It's the same thing. Write down what you have. It is this. The G comes out from here, also from here. It will be the same tautology. There's nothing surprising here. But it turns out that this is half of what we need, this construction. So I want to give you an example. So we already have this G, which acts on S, and therefore acts on functions on S. I'm going to take a very simple G set. Let's take 1 point. And let G act on this. It has to act trivially, right? Tau of this point is equal to this point. There's nothing else. And I want to compute X, tensor product over G, this is S, with this X. So this is X times S. X is a point. So as a set, this is just a point times the square. So this is the square. But I'm modding out by these relations. And these relations are, so the only thing here is tau, and the only thing here is the point. And now for every, let's say, point in the square, this should be equal to tau p. I can move this tau. But tau of a point is just the point. So eventually what I do is the square, and I'm identifying p with tau p. So what I'm going to get is half a square, because this half folded over this guy and I identified them. So it's not that terrible when you write it down. It's a very simple example, but if you have more elements, you get more copies and more identification, and it's just gluing things. Like big. If my student, if I had this in my class, they would hate me. That the only time they have to sing is when I'm. Okay, what I want to show you is this. So we should have now that function from x over g to r. So x over s to r should correspond to functions which are g with respect g from x to functions on s. This is the main thing. What happens here? So this x is just a point. This is a square. And we said that this was half a square. Why is that true? Why does half a square, function on half a square, correspond to function from this point to function on the entire square? Because of this g. This g means that the scalar tau should be preserved. So here I need to choose where I send this point. So I need to send this point to some functions from the square to r. But I have this g, which means that I should have tau of the point equal to tau of f, and tau of the point is just the point, which is f. So my f has to respect tau, has to be preserved under tau. This means that this f should be symmetric under the flip. And if f is symmetric under the flip, it means that it's enough to take half the square to encode it. That's what's happening here. So this is half of the construction. Eventually what we're going to take, okay, so I'll give the recipe. We're going to take a group G acting on some geometric shape. We're going to take two G set with some special property. This is what I still need to explain. And we're going to get that the tensor product of x and of y with this geometric shape over the group has the same sound. So what is this magic property?
And G is general or this very special?
What?
G is a general group?
Anything.
Not as this example.
No, anything. This is, you can definitely get the drums I showed you earlier, the green and the purple one from this. And the group you'll use will be ESL3 for that.
So this is a new approach to constructing this example?
It gives you everything which is Sonata. This is a generalization of Sonata. So everything to do with Sonata.
Can you get something even simpler than Sonata with this approach?
In some sense, yes. Okay, so here's the property. So again, back to algebra. I'm going to need another magic from algebra, which is the following. Function from, so this is the set, and V will be a vector space.